All right, L'Hopital's rule. If you want to find the limit and there's lots of zeros in it, L'Hopital, L'Hopital, L'Hopital. So, oh, by the way, as far as L'Hopital goes, the S, and I learned this from my French students, the S needs to be there because we don't have the hat on the O. But if we have the hat on the O, we would not put the S. And yes, it does have literal meaning, the hospital. It is some person's last name who had a part in this rule. So here we go. You have limit as x approaches a of f of x divided by g of x. Now I want to first show you an explanation of why this rule works and why you have to have the particular situation for it to work. It's not a proof, but it's a pretty darn good show. So, f of x. If I look at the tangent line, tang line, well, we'll take that. Tangent line at x equals a for f of x. I'm going to start off with saying that it's y minus y coordinate equals slope times x minus x coordinate. If the x coordinate is a and the function is f of x, then the y coordinate is f of a and the slope is f prime at a. And on that tangent line, any y value can be approximated. On the tangent line, it is equal to f of a plus f prime of a times x minus a. The function near a can be approximated by this tangent line. And I want to make sure to clarify, near x equals a, you can say this. And if I'm looking at a limit as x approaches a, am I dealing with x's near a? Yeah, I am. So here's what it is. The limit as x approaches a of f of x divided by g of x is approximately the limit as x approaches a of, now, f of x's approximation is this whole piece right here. So f of a plus f prime of a times x minus a. Similarly, g of x, green for g because it's g. G is approximately g of a plus g prime of a times x minus a. If f of a and g of a are both equal to 0, as you see in this picture. Then when I come back over to this approximation, and I replace these two with zeros, I lose the addition in the numerator and the addition in the denominator that holds me back from being able to cancel x minus a. With those two being equal to 0, I can cancel x minus a, and I can say that this limit is approximately the same thing as the limit as x approaches a of the derivative of f of a over the derivative of g of a. And we then take this and move it out to back to x, because I mean, if you look at it, that's basically the same thing. I replaced the a with an x because x is approaching a. This is not a proof, but this is a pretty good show. Again, it is a very good showing why L'Hopital's rule works. But I want to emphasize, if they are not zero, you don't get to cancel and you don't get to say this at all. So the painful part of L'Hopital is properly writing it all out. The joy is getting to use it. So here's L'Hopital's rule. If both of these are true, and I'm going to get to the other part. If both of those are true, then this is true. But they must both be true in order to use L'Hopital's rule. And now I'm going to talk to you about the fact that 0 over 0, well, we've talked about before that 0 over 0 is an indeterminate form when it comes to limits. Infinity over infinity is a similar indeterminate form, and I'm going to show you just how similar. Are you ready? So, 0 could be rewritten as 0 divided by 1. I'm going to now do a fuzzy equal sign. By fuzzy, I mean, I'm kind of playing with zeros and infinities, and this gets fuzzy. Now, if I have a fraction over a fraction, I can reciprocate both and change their side of the fraction and have the same exact number. So what I'm saying is, if I take this 0 divided by 1 and I move it to the denominator as 1 divided by 0, if I take the numerator and reciprocate it to the denominator, it's the same thing. And then I take this denominator and reciprocate it to the numerator. And then I look at what that gives me. 1 divided by 0 is what idea? Infinity. So really, a 0 over 0 situation is also an infinity over infinity situation. You can take any fraction and double reciprocate, and it's the same fraction. It's just not as pretty anymore. But we're not going to, judge those poor little fractions. Sometimes more complicated is pretty. So we are ready for an example. Oh, and I should mention, the infinity over infinity situation, it does not matter if either of them is positive or negative or same sign, opposite sign, it doesn't matter. When you're dealing with 0 over 0, you actually have positive, negative issues going on. You just don't realize it. Because 0 has a positive side and a negative side, and you've got two zeros, each of them having a positive and a negative side. So these are the two indeterminate forms you want to be familiar with. Now, on the AP exam, if you do not properly justify your use of L'Hopital's rule, you might as well have not L'Hopital'd at all. Make sure you are clear about this, and I will push it on the test. So I cannot just go, I'm going to start L'Hopital'ing right now. I'm just going to derive. No. You're going to first state that you are allowed to use L'Hopital by writing out limit as x approaches 1 of natural log of x is, what's the natural log of 1? 0. And write out the limit as x approaches 1 of x minus 1 is, shocking, 0. Because of that, I am allowed to L'Hopital. I recommend it is better form if you say that you are L'Hopitaling. So this is said first, then you say, I'm going to L'Hopital. I'm abbreviating because I want to. So L'Hopital's rule says the limit as x approaches 1 of the natural log of x over x minus 1, knowing this information, is allowed to be equal to the limit as x approaches 1 of. And don't quotient rule this. You're going to be tempted, but make your life happier. Derivative of the numerator. Derivative of the denominator. And now try plugging 1 in. And yeehaw, look at that. We got a limit. And guess what this means? This means that now you can sketch the graph of this function. Come on, see the happy. Oh, I didn't see happy faces. So in section 4.3, you are doing graphs. And I even gave you a hard one last night where you had to deal with asymptotes that you were already able to find. Before we go on to section 4.5, we have to do this section because there are some graphs you're not going to be able to determine asymptotes for until you learn L'Hopital's rule, to learn a nice way to find limits of functions where you can't just algebra power your way through it. All right, it's time for another example, and then we'll do another example, and then we'll do another example, and then we'll do another example. Yay. All right, I'm going to erase what is coming down here. All right, here we go. What's the first thing you're going to write down? You are going to sit here and say what each individual limit is. Do not start off the fraction, start off the individuals. You have to know your graphs of all your functions. E to the x, here's a sad version of it, but exponential functions, asymptote on the left end, head to infinity on the right end. The answer to this limit is infinity. X squared, no need to explain, it's infinity. So this time we have the infinity over infinity situation, and L'Hopital's rule says, go for it. Do it. Do it. So we must lope it. It seems that particular phrase has left teenage lingo. A long time ago, I would always say, lope it. And then all of a sudden one day, students started laughing hysterically. And apparently that had some teenage lingo to it. And I've been finding, I think last year was the first year that people were like not laughing about it. And I'm like, oh, lingo changed again. When I was growing up, everything was rad. That's so rad. That's radical. And I remember a teacher telling us that when they were growing up, people would say cool. And we're like, weird. And then cool came back and rad just ratted its way away. Much to the Vans company's sadness. Okay. So here we go. L'Hopital. The limit we began with is equal to derivative of e to the x, derivative of x squared. And then we go, yeah, plug it in. And then we go, wait a minute. Is this a trick? No, it's not a trick. It's just a kind of loop. You might call it a L'Hopital loop. Let's loop it again. So, new limit. Again, the limit as x approaches infinity of the numerator of the limit I am trying to solve is equal to infinity. The limit as x approaches infinity of the denominator is infinity. I'm allowed to L'Hopital. Let's go. Lope it, lope it, lope it, lope it. So, limit as x approaches infinity of what we started with is equal to, and then derivative of the numerator function, derivative of the denominator function, and then you're like, come on, let's work. I don't want to do this again. And then you go, yes, done. This is infinity divided by 2. That's infinity. All that work to find out we have a does not exist situation. Yeah. But wait till the next one. Next one gets better. Or maybe it's the fourth one. We'll see. And it looks like people are still writing. Totally tubular. Oh my goodness. That takes me back. Okay. Here we go. Oh yeah, it's number 4 that's going to get super exciting. This one's just it's nice. It's nice. So again, let's check. Limit as x approaches infinity of natural log x. We're getting infinity because we know the graph of natural log. We also know the graph of cube root x. And let me just point out to you, you should remind yourself what these look like. Natural log has its little asymptote, and it grows super, super, super slow, slower, 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 but never stops growing. And that's why we actually do get infinity. Cube root of x isn't exactly the fastest function in the bunch. It goes, it's like a totally tubular time going, hey man, I'm growing. Stick around. I will. They both head to infinity at their own little pace. So this means I'm allowed to L'Hopital. So here we go. Seat belts on. Limit as x approaches infinity of the function we began with is equal to the limit as x approaches infinity of derivative and derivative. Now we're in a situation where we don't know if we need a L'Hopital again, but we do need to simplify this and figure out what's going on. So now the equal sign is not the L'Hopital. This equal sign was the one that went through the magic. This one is just trying to figure out, wait, where do I go? It's like a bunch of kindergartners not knowing where they're going, and you're trying to tell them where to go. That's chaos. So this 1 over x can reciprocate to the denominator and be just plain old x. In the denominator, I have the fraction 1/3. That fraction can reciprocate up to the numerator and be 3. Anytime you change the side of a fraction that a number is on, if you reciprocate it while you change the side, it's the same thing it was before, just in disguise. Then I have a negative exponent. That means that moves up to the numerator with a positive exponent. And I can oh, heresy, heresy. I didn't write limit in front of that. That's like a mathematical sin. Okay. Whew. Okay. Simplifying a little bit further, we get the limit as x approaches infinity of 3. And I want to write this where it has its positive exponent. In the denominator, it has a positive 1/3 exponent once it's simplified. And now, throw that infinity in. And all that work for nothing. I always find it amusing when you do an insane amount of math and wind up with the answer 0. Ratitadical. Okay. Now for the fun one. I need to move this up. I say fun. You tell me what you think afterward. Yeah. Alrighty. We must, before we start, justify our L'Hopitalling. If we L'Hopital, that is. So I need to remember, what is tangent? What does its graph look like? So I'm going to do a real quick drawing of a tangent graph. You should recall that it goes through the origin and it goes wee, 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 wee. Every n pi over 2. Okay, so tangent of 0 is 0, 0 minus 0 is 0, 0 it is. Then limit as x approaches 0 of x cubed. I plug 0 in, I get 0 out. This says, you may L'Hopital. And here we go. Limit as x approaches 0 of tan x minus x over x cubed is equal to, I'm going to have to erase my tangent graph. Limit as x approaches 0 of derivative of tangent is secant squared minus 1 and derivative of that denominator. Yeah. What's the secant of 0? Secant is the reciprocal of what function? Who is secant's reciprocal? Right, cosine. And cosine starts at 1 and then does its lovely wave. So that means that at x equals 0, secant is the reciprocal of 1, so it's 1. And then I square the 1, and it's a 1. And then I subtract the 1, and I have to lope this again, don't I? Yes, you do. So here we go again. The limit as x approaches 0 of secant squared minus 1 is equal to 0. Limit as x approaches 0 of 3x squared is 0. You may L'Hopital. So that limit as x approaches 0 of secant squared x minus 1 over 3x squared is equal to, I'm erasing this graph. Low bit. Oh dear. Derivative of secant squared. Got a little chain rule action. So I'm taking the derivative of blah squared. I first use the power rule. Derivative of blah squared is 2 times blah. Chain rule says, give mommy her baby. And then we multiply by the derivative of that baby. Derivative of secant x is secant x times tangent x. Yes. Minus the derivative of 1. Done. And then derivative of 3x squared is 6x. Whew. All right. Excellent. Now let's plug 0 in and get something. I'm looking at your faces, seeing when the moment hits you that you realize we have to do it again. That's just so funny. I love this problem. It's the best example ever. So the limit as x approaches 0 of, and I'm going to write this as 2 times secant squared x times tangent x. While plugging 0 into secant gives me 1, plugging 0 into tangent gives me 0, and 0 times 1 times 2 is 0. And the denominator function is heading to 0. So we are all clear. L'Hopital, come on out. I'm just going to say we are here, and now let's L'Hopital. So I need to take the derivative of secant squared again, but when I'm in the middle of a product rule. So here we go. I'm going to say this is one of my 2 functions multiplying. This is my other one. So I'm going to keep the first one, multiply by the derivative of the other, and derivative of tangent x is secant squared. Plus, this time I'm going to keep the tangent x and take the derivative of that first function, realizing that, again, this is a situation of chain rule. Derivative of 2 blah squared is 4 blah. And then I give mommy her baby, and I multiply by the derivative of that baby, which is secant x tangent x. Nice thing about computer is it doesn't have an end like paper, and I can move it. Usually at this point, I'm drawing down the side of paper, which maybe you are because maybe you're using paper. All right, so we did the derivative of that top function and now derivative of the bottom function. Cross your fingers. If there was another L'Hopital, would you quit right now? Let's keep in mind that when we plug 0 into tangent, we get 0. So this tangent is multiplying to all of this. So all of that is 0. And right now, the clouds should be parting for you. And the sun is shining down through that little hole in the cloud, and you're going, oh, I see it. I see it. Secant of 0 is 1. So I've got 2 times 1 squared, or 2, divided by 6. I can stop writing limit at this moment because I'm answering my limit, but I'm not allowed to stop writing limit anytime before then. And I get 1/3. Bam! Take that, Trig. I own you. All right. Okay, are you getting really, really tired of having to write out the full L'Hopital rule? Okay, why don't we just do it? Go, L'Hopital. Just go, L'Hopital. I'm tired of doing this. No one's going to make me write limit every time. No. So L'Hopitalene, I get derivative sinus cosine, and positive sign. And then when I plug in pi, sine of pi gives me 0. Oh no. Cosine of pi gives me -1. Oh yes! Woo! Infinity! Woo woo! Woo woo! Woo woo! Anyone gonna stop my excitement? Oh, yes. Do you have a problem with that, Jacqueline? Because
Well, it's a left-sided limit, so you have to look at both sides of it, or?
With the left-sided limit, what you have is technically this sin x, if I'm coming from, let me draw, if I'm coming from the left side of pi, sine is a positive number heading to 0, so I'm getting a positive 0. So it's negative infinity, to be more precise. But is that okay? Anyone have a problem? No one has a problem? So the sine of pi is heading to 0 from the left, but it's heading to 0, right? Divided by 1 minus, and this problem is a little bit cruel right here with the negatives, but what's the cosine of pi? Cosine of pi is -1. Take a good look at that. What is the actual answer? It cannot L'Hopital. You must always check, no matter how tired you are, because you know that it's that time when you're too tired to do it that it finally comes out. So this is actually 0 divided by 2. The answer to this limit is 0, but by L'Hopitalene I wound up with a does not exist. So the moral of the story is always L'Hopital. Okay, I am running out of time and I need to very quickly talk about other indeterminate forms. However, you need to start your quiz. So I think what I will do is I will need to make a second video where I finish these notes for you. And make sure you watch it.